Exploring Grover's algorithm, a quantum search experiment. This is Professor Atif Reed Mohammed. This is a series of Masters in Quantum Computing at Marshall University, Lecture 8. Today we are going to explore one of the coolest ideas in modern computer science, a quantum algorithm called Grover's algorithm. Don't let the name scare you. By the end of this class, you will actually understand how it works and why scientists are so excited about it. Quantum computing is a completely new way of processing information instead of using the regular computers we are used to. Quantum computers use the strange rule of physics to solve certain problems much faster. As Einstein once said, the spooky action at a distance. It is like upgrading from bicycle to a rocket ship for specific types of problems. Okay, this means that we are ready to handle some big ideas. We'll take it step by step, do some hands-on activities, and even have some understanding in terms of discussions. Let's get started. You might be wondering, why should I care about a quantum computing algorithm? Well, quantum computing is one of the fastest growing fields in technology right now. Companies like Google, IBM, and Microsoft are spending billions of dollars in it, and governments around the world are racing to develop quantum computers. Grover's algorithm is a perfect starting point because it solves a problem we all understand is searching for something. If we have information, then we have to search what we need from that. Whether it is finding a contact in your phone, a song in a playlist, or a medical record in a hospital database, searching is something computers do billions of times every day. Today we'll learn how a quantum computer can search through huge amounts of data far faster than a regular computer. You'll also compare the two approaches side by side so you can really see the difference with your own eyes. So quantum is the future. Quantum computing is revolutionizing computation as we know it. Game-changing search. Grover's algorithm dramatically speeds up searching large datasets. And today's goal is to explore how it works, why it matters, and apply it to real problems. So as we have been discussing, classical versus quantum computing, classical is 0 or 1, qubit comes 0 plus 1 plus infinity and beyond. Both states at once. And in the case of classical, it's n steps, and in the case of quantum, it's the square root of n steps. What we'll learn today or in this lecture, by the end of this lesson, you should be able to explain that Grover's algorithm is and what problem it solves. You don't need to memorize every detail. The goal is to understand the big picture and be able to explain it to someone else in your own words. You will also be comparing two ways of searching, the classical method that regular computers use and the quantum method that Grover's algorithm uses. Understanding the difference between these two is the heart of today's lesson. You will also get to apply what you have learned through two activities, a search race and a quiz. Learning is always better when you are doing something, so get ready to participate and have some fun with it. Picture this, you are handed an old school phone book with 1000 names listed in random order, not alphabetical, just completely shuffled. Someone asks you to find John Smith. How would you do it? Now that's a good question. Think about it. Most people would just start at page 1 and check every single name until they found it. That might not seem so bad with 1,000 names, but what if the phone book had 1 million names or 1 billion? Suddenly, checking every name one by one would take an extremely long time. This is actually a real problem that computers face every single day when searching large databases. This scenario is exactly the kind of problem Grover's algorithm was designed to solve. Keep this phone book example in your mind as we go through the lesson. It will help everything else much more sense. So, as the slide says, how would you find John Smith? First, check every name one by one. Second, use an index or shortcut. Third, use a smarter algorithm. A classical computer, which is kind of computer you use every day, searches through data by checking items one at a time. It starts at the beginning of the list, looks at the first item and asks if this is this the one I'm looking for? If yes, great. If no, it moves to the next one and checks again. This process is called linear search, and it's actually very simple and reliable. The problem is that it does not scale well. As the list gets longer, the number of checks grows at exactly the same rate. Double the list size and you double the time it takes. For a list of 1,000 items, a classical computer might need up to 1,000 checks to find the right one. That's manageable, but if the list is in millions, as I discussed earlier, this is where things start to get slow and inefficient. So on the slide, you're looking at linear search, check items one by one and cross it. When you find it, that's it. So there are two lists now. One is already checked, one is found here, and one is unchecked. So items checked one by one in a sequence as linear search, up to n checks needed for n items, called linear search O of n complexity. The core limitation of classical search is that it grows in a straight line with the size of the data. Computer scientists call it the linear time, or ON complexity, where n is the number of items you are searching through. The bigger n gets, the slower the search becomes. In the real world, database can maintain hundreds of millions of or even billions of records. Think about how many patients are in our national healthcare database, or how many transactions a bank processes every day. Checking every single one of them to find match would be incredibly slow. This is not just a minor inconvenience. It is a major bottleneck in computing as the world generates more and more data every year. We desperately need faster ways to search through it. That's exactly the problem that quantum computing and Grover's algorithm specifically is trying to fix. So the problem is slow for large data sets. Time scales linearly with n. 1 million items is equal to up to 1 million checks. Impractical for modern data volumes. Imagine the nonsense of Amazon delivers every day the packages. Millions of packages are delivered on everyday basis. Grover's algorithm was invented in 1996 by a computer scientist named Love Grover, L-O-V, while he was working at Bell Labs in the United States. At the time, the idea of quantum computing was still very theoretical, but Grover showed mathematically that a quantum computer could search an unsorted list much faster than any classical computer. What makes this algorithm special is that it works on unsorted data. You don't need to arrange your list in any particular order or for it to work. It uses the unique properties of quantum mechanics, things like superposition and amplitude amplification, to find the answer in far fewer steps. The algorithm is also considered provably optimal, which means mathematicians have proven that no quantum algorithm can search an unsorted database faster than Grover's algorithm. It is not just a good solution, it is the best possible quantum solution to this type of problem. So that's it uses a quantum superposition, square root of n step complexity, widely studied algorithm, and provably optimal. So again, Love Kumar Grover, a landmark quantum algorithm it is. To understand Grover's algorithm, you first need to understand what makes a quantum computer different from a regular one. A regular computers store information in bits, as we discussed earlier, tiny switches that are either off, 0, or on, 1. Every piece of data, every calculation, and every instruction is made up of these simple zeros and ones. A quantum computer uses something called qubits instead of regular bits. A qubit is special because it can be in a state of 0, a state of 1, or and this is the mind-blowing part, both 0 and 1 at the same time, as the superposition, as we have been discussing in our previous discussions. This is called superposition, and it is one of the key principles of quantum physics. Because qubits can hold multiple states at once, a quantum computer can process many possibilities simultaneously. It is like being able to check multiple items at the same time instead of one at a time. This is a fundamental reason why quantum computers can be so much faster for certain tasks. Now let's expand on superposition. Superposition is one of the strangest and most fascinating ideas in all of the physics. And since we have discussed superposition in quite detail, so I am going to bring in physics rather than the computer science here. It means that a quantum object like a qubit can exist in multiple states, as we discussed earlier, at the same time, right up until the moment you actually look at it or measure it. Once you measure it, it instantly picks one definite state, as we had been discussing in quantum automata. A helpful way is to think about spinning coin, as we discussed and practiced in our earlier discussions. While the coin is spinning in the air, it is neither heads nor tails. It is kind of both at once. The moment it lands on the table, decoherence happens. It becomes one or the other. A qubit is similar. It is multiple states while you are computing, but picks a single state when you measure it. I am bringing this discussion again and again to make sure that you have grasped the idea and your comprehension is clear. In the language of quantum physics, a qubit state is written as in the oval. So it's in reality the state, as we discussed earlier. You can write it as you like. So you can also write the pipe sign q and the greater than and alpha, pipe sign 0 greater than then plus beta, pipe sign 1 and greater than sign. So don't worry too much about the symbols. What it means that the qubit has a certain probability of being 0 and certain probability of being 1. Grover's algorithm is clever because it manipulates these probabilities to make the correct answer much more likely to appear. In Grover's algorithm, the question is, what is an oracle or quantum oracle. In Grover's algorithm, quantum oracle is a special part of quantum circuit that knows what the correct answer looks like. Think of it as a judge or a referee. It can recognize the right answer when it sees it, but it does not tell you what the answer is directly. The oracle works by flipping the phase of the correct answer in the quantum system. Phase is a mathematical property that does not change the probability directly, but it is used in the next step, amplitude amplification. To boost the correct answer's chance, it is a bit like marking the right card in a deck with a tiny invisible dot. Without the oracle, the algorithm would not know which answer to look for. The oracle is the part of the system that encodes the specific problem you are trying to solve. For different search problems, you would use a different oracle, but the rest of the Grover's algorithm stays the same. Imagine you're playing a guessing game with a friend. Your friend thinks of a secret number between 1 and 100, and your job is to guess it. Normally, you would have to ask, is it 5? Is it 12? And so on. And one number at a time. This could take forever. Now imagine that your friend has a magic box that lights up only when you say the correct number. The magic box is like an oracle. It does not tell you the answer, but it gives you the signal when you are right. In Grover's algorithm, the oracle works in the same way. It does not know the answer, but it can mark the correct one in the list of possibilities. For example, if you're searching for a specific name in a phone book, as we discussed earlier, the oracle would light up when it finds that name, John Smith, helping the quantum computer focus on the right choice faster. Without the oracle, the computer wouldn't know which answer is correct. Amplitude amplification. Amplitude amplification is the step in Grover's algorithm where the magic really happens. After the oracle marks the correct answer, amplitude amplification uses a mathematical technique to increase the probability of measuring that correct answer. Everything else, all the wrong answers, get pushed down in probability. Think of it like turning radio. When you are searching for a specific station, there is a lot of noise and many different signals. Amplitude amplification is like turning up the volume on exactly the right frequency and turning everything else down, so the signal you want comes through loud and clear. I hope you have used radios once upon a time, blue moon ago. The clever thing is that you repeat the oracle and amplification steps multiple times. Each repetition pushes the correct answer's probability higher and higher, while the wrong answers get less and less likely. After that, the square root of n repetitions, the correct answer has such a high probability that when you finally measure the qubit, you almost always get the right result. Let's look at another example. Imagine you are at a carnival playing a game where you have to pick the one red ball out of the giant bucket of blue balls. At first, all the balls look the same because they are mixed together, and it is hard to spot the red one. But what if you had a special flashlight that made the red ball glow brighter while keeping the blue balls dim? Suddenly, the red ball stands out and you can grab it easily. Amplitude amplification in Grover's algorithm works like that flashlight. The quantum computer starts with all possible answers mixed together like the balls in the bucket. The algorithm then turns up the brightness of the correct answer, making it much easier to find. This way, the computer can quickly pick out the right solution from all the possibilities, just like spotting the glowing red ball. So, you just have witnessed in the slide how it happens. Grover's algorithm works in a series of clear steps. First, you put all n possible answers into an equal superposition, meaning every possible answer starts with the exact same probability of being selected. This is like shuffling all the cards face down and giving each one an equal chance. Next, the oracle marks the correct answer by flipping its face, and then amplitude amplification boosts the answer's probability while suppressing all the others. These two steps together, oracle then amplification, are called one iteration of the algorithm, and you repeat them approximately square root of n times. After all the iterations are done, you perform a measurement. Because the correct answer has been boosted to a very high probability, you almost always measure the right result on the first try. The whole process finds the answer in just square root of n steps instead of the n steps a classical computer would need. Let's take another example that you are trying to find a specific item in a messy box of items in your garage. Instead of digging through one item at a time, you shake the box in a special way so that the item you want rises to the top. Grover's algorithms works in a similar way, but instead of shaking the items box in your garage, it uses the power of quantum computing to highlight the correct answer or correct item. Here's how it works step by step. First, the algorithm puts all possible answers into a quantum state, like mixing all the items together. Then it uses a special process called an oracle to mark the correct answer or correct item, just like putting the bright sticker on that item you want. Next, it amplifies the marked answer, making it stand out from the rest. Finally, the algorithm measures the result and the correct answer is revealed, just like pulling the right item out of the box in your garage. So these are the steps that how it works. So why is it faster? The speed advantage of Grover's algorithm comes from a mathematical concept called square root scaling. A classical computer needs up to n steps to search n items. Grover's algorithm only needs approximately square root of n steps, and square root of n is always much smaller than n, especially for large data sets. So here's a concrete example to make it real. Suppose you have 1000 items. A classical search might need up to 1000 checks. Grover's algorithm only needs about square root of 1000, which is roughly 32 steps. That means Grover's is about 32 times faster than for this example. For 1 million items, the classical computer need to 1 million checks, while Grover's only need about 1000. That's 1,000 times faster. Computer scientists describe this as a quadratic speedup. It is not as dramatic as some other quantum algorithms. For example, Shor's algorithm gives an exponential speedup for factoring numbers, but for searching problems, it is the best any quantum algorithm can do, and it is still massive improvement over classical methods. Let's change the idea that let's say you're searching for your favorite song on a music player. If you had to listen to each song one by one, it could take a very long time, especially if you have thousands of songs. For example, if you have 1000 songs, you might have to listen to all 1000 before finding the one you want. This is how classical computers search. It checks each item one after another, as we are discussing in this lecture quite often, until it finds the right one. Grover's algorithm is like having a super smart music player that can narrow down your favorite song in just few guesses. Instead of listing 1000 songs, it might only take around 32 years, so 32 tries to find the right one. Since the square root of 1000 is about 32, this huge shortcut is what makes Grover's algorithm so powerful. It does not have to check every single item, just the most likely ones, saving a tons of time. Let's make it so real world example of a deck of cards, for example, if we go through that route. Let's make this really concrete using a deck of playing cards. Let's say you have a standard shuffle deck of 52 cards, all face down, and your job is to find the ace of spades. Classically, you would flip cards one at a time. You might get lucky on the first try, or you might have to flip all 52 on average. You would flip about 26 cards. Now imagine using Grover's algorithm on same problem. You would need approximately square root of 52 steps, which is about 7.2, so roughly 7 steps. That's nearly 4 times fewer steps than the classical average. For a small deck of cards, it does not seem life changing, but the scale that up to million of cards and the difference becomes enormous. This card example is also a great way to understand why Grover's algorithm is described as working on unsorted data, as we are discussing in this lecture in quite depth. The cards are in a random order. There is no pattern or structure to exploit. Grover's algorithm does not need any order or structure. It works through quantum mechanics alone, which is what it makes powerful so in general. So let's change the pace. You are in a library with 100 books, and you need to find one specific book with a blue cover. If you check each book one by one, starting from the first shelf, it could take up to 100 attempts to find it. That's how a classical computer searches, as we have been discussing in this quite in depth. Slowly and methodically. Pardonnez-moi, pardon my English or French. Like scanning every book until you finally spot the blue one. Now think you have a helpful librarian who can instantly group the books into smaller piles of 10 books each. Instead of checking all 100 books, you only need to look through about 10 piles, since the square root of 100 is 10. Grover's algorithm works like that helpful librarian. It narrows down where your book is hiding, so you find it in just a fraction of time. So the use of Grover's algorithm in the industry. One of the most exciting real-world application of Grover's algorithm is in database searching. Hospitals, for example, keep enormous databases for patient records. If a doctor needs to find all patients with a specific rare disease among millions of records, a classical search could take a very long time. Grover's algorithm could dramatically reduce that time. The same idea applies across many industries. In cybersecurity, Grover's algorithm could be used to search through possible passwords or encryption keys much faster than classical methods. In logistics, it could help companies search through millions of routes or inventory records to find the optimal solution. In finance, it could scan massive transaction records to detect fraud. It is important to note that we are not quite there yet in terms of real hardware. Today's quantum computers are still too small and noisy to run Grover's algorithm on truly large databases. But as quantum hardware improves over the next decade or so, these applications are expected to become very real and very impactful. So, healthcare, logistics, cybersecurity, finance are some of the examples. So, let's experiment. Now it is time to stop listening and start doing. You're going to experience the difference between classical and quantum search firsthand through two activities. The first is a search race where one team uses classical search and another uses a strategy that stimulates quantum search to find a hidden number. The second activity that I will actually bring it on is asking a question or formulating a research question where you will work in groups to answer questions about Grover's algorithm as fast as you can. This is your chance to test what you have learned and see how well you understand the key ideas from the lesson. Both activities are designed to be fun and competitive, but they also have real educational purpose. Research shows that you learn and remember things much better when you actively apply them, so take both activities seriously. Ready? Let's go. Okay, here is how the race works. Your class will be split into two teams, Team Classical and Team Quantum. So think of you as either Team Classical or Team Quantum as one man show for the sake of learning at this very moment. So both teams are trying to find hidden target number among 16 face down index cards. The number could be anywhere. The cards are in completely random order. Team Classical will search the old fashioned way, flipping cards one at a time. Team Quantum will use a different strategy that mimics how Grover's algorithm works, dividing the cards into groups and checking multiple possibilities at once. Both teams start at the same time and will track how many steps each team needs. So pay close attention to how many steps each team takes, Team Classical and Team Quantum. You can be as an individual or Team Classical or Team Quantum. Choice is yours to make. Because after the race, we are going to compare the results and talk about what they mean. This activity is a simplified version what quantum computer actually does. So it is a great way to feel the difference between two approaches in a real physical way. Okay, Team Classical rules. Your job is straightforward. You will receive 16 face down index cards, each with a different number from 1 to 16 written on it. One specific number has been chosen as a target. Your job is to find it by flipping cards one at a time. Every time you flip a card and it is not the target, count that as one step and move on to the next card. You can flip by the cards in any order as you like. There is no rule about which one to flip next. Keep an accurate count of every flip you make because that count is your final score. You stop the moment you find the target card and you record how many flips it took. In the best case scenario, you might find it on the very first flip. In the worst case, you might flip all 16 cards on average and you would be expected to need about 8 flips. Remember this number when you compare the results at the end. So these are the 5 classical rules. So receive 16 face down index cards, number 1 to 16. Flip cards one at a time in any order as you choose. Count the record every flip you make. Stop as soon as you find the target number. Record your final flip count for comparison. Expected outcome up to 16 flips. So that's your Team Classical rule. Team Quantum rule. Team Quantum, So if you made yourself as Team Quantum, for example. Team Quantum, your approach is different and represents how Grover's algorithm works. You will receive same 16 face down cards, but before you start, you will divide them into four groups of four cards each. This grouping represents the way a quantum computer considers multiple items simultaneously. Your first move is to reveal all four cards in one group at the same time. That counts as one step. This counts as one step. If the target is in that group, you then narrow down within the group. If the target is not in that group, you move to the next group and reveal all four cards there, but and that's your second step. Technically, it's your next step. You continue this process one group at a time until you find the group containing the target. In the best case scenario, you find in the first group one step. In the worst case, check all four groups, four steps. So technically square root of 16 is 4, which perfectly matches the Grover's prediction. Compare your result to Team Classical. You might be Team Classical simultaneously, Team Quantum, as per your own choice. And think about what that tells you. When you compare the results from both teams, you can play as both teams one at a time. The pattern should be clear. Team Classical might have needed anywhere from 1 to 16 flips with an average around 8. Team Quantum, following the Grover's inspired strategy, needed at most 4 steps, which is square root of 16 for the same problem. The quantum approach is significantly faster. This difference might not seem huge for just 16 cards, but think about how it scales if there are 10,000 cards. Classical search would need up to 10,000 checks. A quantum search would only need about 100. If there were 100,000 cards, classical needs 100,000 checks, and quantum only needs 1,000. The bigger the data set, the more dramatic the advantage. The key reason Team Quantum wins is that their strategy checks multiple cards at once, whole groups at a time. This is exactly how a quantum computer uses superposition. Instead of looking at one possibility at a time, it considers many simultaneously, which is what gives it speed advantage. So, alright, it is time for the quiz. You are going to work in your groups to answer 10 multiple choice questions about Grover's algorithm. The questions cover the key ideas from today's lesson. Things like superposition, the oracle amplitude, amplification, and the speed comparison. You have exactly 3 minutes to answer as many questions as possible. Speed matters, but so does the accuracy. So in this case, we can establish, rather asking questions, a discussion. And this is a great study technique. That's the experiment design when you do the quiz. Or you can also do the open discussion, explaining ideas out loud to your teammates, or discussing with your teammates is one of the best way to figure out what you actually understand and what you are still a bit fuzzy on. If your group disagrees on some discussion, talk it through. That discussion is where the real learning happens. So what does this matter actually? Grover's algorithm matters because searching is one of the most fundamental things computers do. Every time you type something into a search engine, every time a bank checks for fraud, every time a doctor looks for a patient record, all of that involves searching through data. Making searches dramatically faster has huge real-world consequences. The potential benefits touch many different fields. In medicine, faster searches could help researchers find patterns in patient data more quickly, potentially leading to earlier diagnosis of disease or faster drug discovery. In logistics, companies could optimize routes and inventory in real time. In cybersecurity, security researchers could test the strength of encryption more thoroughly. However, it is also important to understand the limitations. Grover's algorithm only gives a quadratic speedup, not an exponential one. It only works for unstructured search, not for every problem a computer faces. It is a powerful tool, but it is not magic. And understanding those boundaries is just as important as appreciating the power. The common misconceptions. One of the most common myths about Grover's algorithm is that it can break all encryption. That is not true. While Grover's algorithm does speed up the process of searching for encryption keys, it does not break well designed encryption systems. For example, AES-256, which is the encryption standard used to protect most sensitive data today, remains secure. You have just you would have just needed to increase key length as a precaution. Another common misconception is that quantum computers are always faster than classical computers for everything. That is also false. Quantum computers are only faster for certain specific types of problems, like searching, factoring large numbers, or simulating quantum systems. For everyday tasks like browsing the web, writing documents, or playing video games, classical computers are actually better. A third myth is that quantum computers are going to replace classical computers very soon. In reality, quantum computers are still in early development. They are very difficult to build, extremely sensitive to interface, and currently can only handle a small number of qubits reliably. Classical computers will be with us for a very long time. Quantum computers will work alongside them, not replace them. Uh, as quantum computing becomes more powerful, it raises some important ethical and social questions that society will need to grapple with. One of the most discussed concerns is security. Grover's algorithm could make it easier to crack certain types of passwords or search for vulnerabilities in encrypted systems. If a powerful enough quantum computer fell into wrong hands, it could be used maliciously. This leads to a big question. Should government regulate quantum algorithms like Grover's? Or on one side, regulation could help ensure that technology is only used for beneficial purpose and that security systems have time to upgrade. On the other side, regulation would slow down legitimate research and development, and enforcing it globally would be extremely difficult since many countries are independently developing quantum technology. There are no easy answers here, and this is exactly the kind of issue that the next generation of scientists, policymakers, and citizens, that means you can be one of them, will need to help figure out. Today's class debate is a chance to start thinking critically about not just what technology can do, but what it should do and who should get to decide. So let's recap the big ideas from today. Grover's algorithm is a quantum search algorithm invented by Love Grover in 1996. It searches unsorted databases in approximately square root n steps compared to the n steps needed by classical computers. This is called the quadratic speedup, and it is best speed up possible for this type of problem. To make Grover's algorithm work, we need three key quantum ingredients: qubits, that can exist in superposition, an oracle that marks the correct answer, and amplitude amplification that boosts the probability of finding the answer together. These three elements produce a search process that is far more efficient than anything a classical computer can do. Quantum computing is still a young and rapidly developing field, and Grover's algorithm is just one piece of it. But it is a beautiful example of how strange rules of quantum physics can be put to practical use. If today's lecture has sparked even a small amount of curiosity about quantum computing, I would encourage you to explore further, because the future